Sunderland could come today. This is a second try to get her here, which was our fault for not getting her here last year. So, with that, Nick, would you like to give the introduction?
Good afternoon, everyone. Real pleasure for me to introduce my friend Elsie Sunderland, who's assistant professor now at Harvard University, where she kind of sits in two different departments, the School of Public Health, which is actually in Boston, and the Engineering and Applied Sciences, which is in Cambridge. And Elsie, in a way that's fitting because her work is extremely interdisciplinary, and she's engaged in modeling atmospheric and oceanic cycling of mercury and other substances in the global environment, and relating that to human health. And as many people here are aware, mercury, probably more than any other contaminant in the marine environment, has serious implications for public health. And I think Elsie's going to tell us about some of her activities along those lines. So we're very pleased to have her here.
Thanks, Nick. Thank you all for the invitation to be here. It's a pleasure to have this opportunity to talk to you all today. Is the volume okay? Is the mic? Yeah? Is it good? Okay, great. So as Nick mentioned, I work in two different groups at Harvard, the School of Public Health and the School of Engineering and Applied Sciences. And I think Mercury is a nice way of linking those sort of disparate research fields, because it's really and this is in my obviously highly biased opinion, but it's a fascinating element to cycle because it has such an interesting chemistry in the atmosphere, in marine systems, the way it interacts with biological systems, and then the sort of public health implications and also policy applications associated with mercury. So I have a nice narrowly defined talk for you today, as you can see by the title, Global Cycling and Bioaccumulations in Marine Ecosystems, and I'll talk to you a bit about some of the implications for human exposure. I like to usually start any talk about mercury with just let's ground ourselves in why do we care about mercury. It's one of the best known environmental contaminants. You see it in the press a lot. My favorite is every 2 years, I'd say, in the New York Times, you see a groundbreaking study where somebody has found high mercury levels in certain species of tuna. It's really shocking. You know, so stay in your chairs. And that might be a public health concern. But and so my point with this slide is, okay, you've probably all heard about mercury in fish. You've probably heard about fish advisories. Many of our aquatic ecosystems across the country have fish advisories in place. You've probably heard that coal-fired power plants are a source of mercury, because that's the kind of thing that makes it into the media. This is a story that was written about a paper that we published a couple years ago, and I particularly like the headline. It was on a cruise, and I'll talk to you about the data we collected a little bit, but it was a cruise of the North Pacific Ocean where we had analyzed the seawater for total and methylmercury and done some modeling associated with that. But the sort of green wire headline, and this actually made it into the New York Times, was mercury in fish predicted to soar, pollution from Asian power plants threatens children's health. So the point of that being what you get in the media might not be the most accurate information and truly reflect the science in place. And actually, there's one side note. This is a story I love to tell from this, which is we were actually, you'll see the data from this study later, but we were blasted a bit by a media group because this story associated with this research was picked up. So a fisheries lobby group, sort of said, oh, this study has no validity. They didn't analyze tuna, and the lead PI on the ship said, well, we would have analyzed tuna, but we had to eat them on board, so it didn't quite make it into the study. But hopefully we could have written that into a rebuttal. But just, I like to use this slide also in many of my presentations. It's a very simple fact sheet from USGS that got cut off at the bottom. But these are the symptoms that people most often associate with human health impacts of mercury on the human body. So you can see that mercury is a central nervous system toxin. It causes kidney failure and liver failure. I particularly like to use this slide because I enjoy highlighting my two favorite mercury exposure effects from the literature, which are frothing at the mouth and excessive shyness, particularly excessive shyness. So if you've ever, had an awkward social moment, you can be like, oh, damn, I shouldn't have had that sushi last night, right? But on a more serious note, so that these are symptoms associated with acute toxicity, so exposures at very high levels of mercury in adults. And most of our safety advisories, our fish advisories, those are built around more subtle effects associated with neurodevelopmental delays in children. So we're talking about really two different things, and there's a lot of confusion about that. It's obviously propagated by the media. But the safety thresholds that we read about and that you see are built around EPA's reference dose. So it's the level established by a National Academies panel in the year 2000, which is meant to protect children against long-term IQ deficits associated with methylmercury exposure. So those are kind of different things. When you look at adult toxicity, that tends to occur at somewhat higher levels. So these are the safety thresholds that we have. If you look at some of the biomarker data, so just if you look at the bottom for a moment, there's a National Health and Nutrition Exam surveys that takes place in the United States. It's a probabilistic survey of individuals across the country, and they collect biomarker data, including mercury. And you can see from those data that, so between 1999 and 2002, about 6% of women of childbearing age exceeded EPA's RFD for mercury. It's slightly lower when you throw in the 2004 data. But if you look at the number of children affected, then that means it translates into somewhere between 300 and 600,000 children born per year above EPA's RFD for mercury. The higher end of that threshold has to do with the fact that what you see in the fetus is actually a concentration of mercury in umbilical blood. So for the fetus to experience an exposure at the sort of the equivalent to the reference dose, you see the maternal concentration has to be more like 3.4 micrograms per liter of blood rather than 5.8. So you'll get some fluctuation, and this percentage of increase will also go up. So this is the kind of thing that human health people talk about, discuss. The other thing is when you think about regulatory actions, and so we have these safety standards in place which are built around, as I've mentioned, IQ deficits, so long-term neurodevelopmental effects in children. There's also a whole area of research looking at other effects associated with methylmercury exposure in human populations, including cardiovascular effects in adults. And so this slide is a few years old. I like the way it expressed our relative certainty in these effects. So we don't actually use the cardiovascular impacts that have been demonstrated in some studies, so increased incidence of myocardial infarction or heart attack associated with methylmercury exposure in adults. We don't actually use those in regulatory determinations right now, but from a policy perspective, this is really important. So every regulation that we put in place to curb human releases of mercury into the environment conducts a cost-benefit analysis associated with that rule. And the benefits, if you think about the numbers of individuals affected, and I realize that might seem a bit odd to you, but that's how the regulatory world works. If you think about the number of children born per year exceeding the RFD versus the number of adults who could be affected by cardiovascular effects, then that really changes that benefits picture associated with reducing mercury levels in the environment. So from a policy perspective, this is a major driver. And there's other areas of research that are ongoing, so things like endocrine effects and areas like that. Just one final note on the cardiovascular effects. There was a panel, so it hasn't been used in regulatory work yet, but there was a panel that EPA convened, and there was a paper published in Environmental Health Perspectives last year where they basically said, okay, we now have enough confidence in our dose-response relationship between methylmercury exposures and cardiovascular impacts to use that in a regulatory determination. And I think that's really important. So you'll see that weaving its way into the regulatory world. And I think these sort of effects are a nice illustration of the interplay between sort of scientific research and public policy. So I've said that most of the work that we do, or most of the effects that we're worried about, is not about adult toxicity, but this is probably quite close to home for many of you. So one of your alumnus, Rich Galfond, has, you do see these cases of adult acute toxicity associated with methylmercury exposure. It tends to happen in people who consume very large quantities of fish. But you will hear people push back and say, oh, there's never been a documented case of mercury toxicity in the US population in adults. And that's just not true, as you can see by Mr. Galfond's case. There are a number of other high-profile ones that probably, if any of you Google, you will find in, 0.16 millisecond. No, I'm just kidding. Jeremy Piven comes to mind. But so obviously then adult toxicity can occur. The other thing to remember is that when we talk about the toxic effects of mercury, we're really talking about methylmercury exposure. So most of the mercury released into the environment is inorganic mercury. The mercury from coal-fired power plants is inorganic mercury. And the exposure pathway for mercury that we're concerned about is through ingestion of fish. So it's very rare that you'll see somebody with very high levels of mercury unless they have some sort of particular cultural practice where they're using a lot of mercury, or they have some sort of industrial exposure. Then their mercury exposure is through fish consumption, or their methylmercury exposure is through fish consumption. These are more data from the National Health and Nutrition Exam Survey. This is, again, U.S. women of childbearing age. This is blood total mercury levels, and this is their reported frequency of fish or shellfish consumption. And there's some imprecision in how well you can correlate this, because the amounts of mercury in fish vary so much across species, but you can see then basically, this is common knowledge in the field, that the mercury exposure of individuals is basically all from fish consumption minus a little bit of background from things like dental amalgams and things like that. But your methylmercury exposure is really coming from fish consumption. So it's the fish that we're looking at as the indicator of environmental exposure. So that creates, again, an interesting dilemma for policy making. So we've got in parallel right now regulatory actions taking place on a variety of different scales. Just last month, EPA put forward its air toxic standards, which included mercury. And this will regulate for the first time mercury emissions from coal-fired utilities in this country. And there's been a lot of political debate about this because industry feels this is very expensive. And EPA really needs to justify, again, in terms of health benefits, the case for this regulation. There's also work underway through the United Nations Environment Program to develop a global treaty on anthropogenic mercury releases for the first time. This will be ratified by 2013. So this is a really big sort of area of momentum for both the research community and policymakers. And the challenge to the scientific community is, okay, well, so we're going to curb anthropogenic releases of mercury to the environment. Mercury is a naturally occurring element. It has this complex biogeochemical cycle. What effect will these actions have on ecosystems, and what will be the benefits in terms of human exposure? So to answer that question, we really have to go through an analysis of the entire exposure pathway for mercury, which is where a lot of our modeling work comes in. So given what I've just told you, I like to start with this question. Seems quite intuitive, right? Where do the fish that people are eating in this country actually come from? And it turns out, so we talk about mercury as a global contaminant, and everybody thinks about, if you've looked at this at all, so you've got a stable form of mercury that basically becomes well mixed in the atmosphere because of its lifetime. But if you look at the sources of fish that people are consuming in this country, then seafood distribution is also a mechanism for global distribution of mercury. So we're eating fish from many different countries. While I was working for EPA several years ago, I put together this paper which is basically to say, okay, what are the sources of methylmercury intake in the U.S. domestic population? And so this is showing you the fraction of U.S. population-wide intake, and these are the different seafood categories that people are consuming. The colors indicate the locations where those fish were harvested. So imported means beyond the U.S. 200-mile domestic water boundary. Atlantic and Pacific are they're sort of white and blue. And high seas landings means fish caught by a U.S. domestic vessel beyond the 200-mile limit. And so the thing that, again, will jump out at you is, okay, well, almost 40% of the U.S. population-wide intake is coming from tuna, different tuna species. And if you look at the color bars associated with this, again, these are offshore harvests. So this is not a domestic U.S. issue. This is very much a global ocean issue associated with tuna harvests. And these are predominantly marine and estuarine species. And that's an interesting challenge, again, for the research community, because our knowledge of mercury cycling and our scientific research has really been focused on freshwater environments. So the ocean sources and marine cycling and controls on methylmercury production are really poorly defined relative to these environments. So this, I thought, was a good sort of way to focus our thinking. The goal of my work, again, it's very large scale, so I always want to link that entire exposure pathway for mercury. If you want to say, well, how is the environment affecting human exposures, you have to know the ecosystems responsible. So we've been looking at cycling of mercury in different ocean basins, and so we want a number for how much of the mercury exposure in the U.S. population is coming from each type of ecosystem or region. So if you break out those numbers that I showed you a minute ago a little bit further, so this is the total amount of methylmercury consumed in the supply of fisheries that are consumed in the U.S. Each year. And this is their harvesting location. So fresh and farmed fish make up about 15% of the methylmercury intake. Nearshore marine, so this is sort of estuarine harvests, make up, including many shellfish harvests, make up about 8%. And then you're looking at, this offshore ocean contribution. So these, and again, it's because of the high mercury concentrations in pelagic migratory marine species, accounting for almost 80% of the intakes. And this is really dominated by almost 30% from the North Pacific and sort of the South Pacific Indian Ocean at about 25%. So these are our major sort of areas that we want to focus on, I think, in terms of understanding where's the methylmercury being produced, how are these fish picking up the mercury, all these different questions. So here are our research questions, and these are quite broad. I won't possibly answer all of them in this talk. You can sigh a bit of relief there, unless you have until 4, which I do. So the first question being, and this is really a first focus that we've looked at quite a bit. So how has anthropogenic mercury impacted ocean ecosystems? Where are the major methylmercury production regions globally? How long? So this is a really policy relevant question. How long will it take for fish mercury concentrations to respond to changes in atmospheric releases? And that largely depends on where that methylmercury production is taking place again, where it's entering the base of the food web. And then sort of the hot, trendy new topics, I think almost in any field, but it also applies to mercury. What's climate change doing? And how does changes in ecosystem structure and biogeochemical processes on their own, how will that affect bioaccumulation? How will that affect human exposures? And what about future emissions? So that's sort of what I'm going to touch on throughout the rest of my time with you right now. Before I get into sort of some of the questions that we've looked at, I just wanted to give you an overview of the sort of modeling tool that we've been developing in my research group for several years now. So the model that we use is a chemical transport model. It's a global scale CTM. It's called GeoSChem. It's used by over 50 research groups globally for a variety of questions. And what we've added is mercury chemistry. So the model is driven by assimilated meteorological data from NASA. And what we've added, which is unique for mercury, is a coupled biogeochemical simulation of not only atmospheric chemistry, but exchange, so terrestrial atmospheric exchange and processes occurring in terrestrial environments, and also air-sea exchange and cycling in the ocean. And this is really important for Mercury, and you'll see this as we, I show you some of the numbers for the biogeochemical cycle. We have a 3D sort of 3D transport model for the atmosphere. The initial version of the model looks mainly at the surface ocean, and we have more simplistic modeling for the subsurface ocean and deeper compartments. And I won't talk about this today, but our terrestrial modeling I think is quite interesting as well. We've coupled the dynamics of Mercury to a global carbon, to the dynamics of organic carbon cycling, if anyone is familiar with the CASA model. So it's coupling the dynamics and the decomposition of mercury and then re-release to the atmosphere back to the dynamics of organic carbon. And I wanted to give you a couple examples of why for mercury and for many things. So, I work a lot, my training is more in aquatic chemistry than atmospheric chemistry. I'm actually a terrible atmospheric chemist, I'll be honest. But I've been around them for a number of years now. And we speak slightly different languages, and for certain trace gases, as many of you in this room know, it's very important to represent both the atmosphere and the ocean in these kinds of simulations. So here's an example on the atmospheric side about why the atmosphere is so important for the ocean. So we want to understand patterns of mercury loading in the ocean. This is a PhD student working with our group a couple years ago, and so the sort of paradigm in the field for a while was that, okay, so you have the majority of mercury in the atmosphere in the gaseous elemental form. This is the stable form that's released as the majority of emissions from sources. It has a lifetime of 3 to 6 months in the atmosphere, so it becomes well mixed. And its deposition depends on its oxidation to this water-soluble divalent mercury. So the distribution of oxidants, in addition to the availability of mercury that you have in the global atmosphere, really determines the spatial patterns of deposition that you see. And so a lot of the thinking several years ago, and among some scientists still, was that the major oxidants were ozone and OH for elemental mercury. And we think, okay, well, this kind of sounds like a nuance in the field, but if you care about oceans, this has a major impact. The kinetic data point more strongly to bromine as the major oxidant. So we switched the implementation of the oxidant in geochem from OH and ozone to bromine. And you see that has a major impact on the spatial distribution of mercury deposition across the global oceans. And again, you can't see that unless you have these coupled types of simulations. The other project that we've been working on that I think really makes a strong case for this type of coupled modeling framework is in a project we have ongoing in the Arctic right now, modeling mercury cycling in the Arctic. The behavior of mercury is quite unique in the Arctic. So you have, with sea ice melts, you have these bromine explosions, and bromine, as I just mentioned, is a major oxidant for elemental mercury. This is quite famous. You get these atmospheric mercury depletion events. So you can see this. The black is the observational data. So these are atmospheric mercury concentrations. This is by season. Sorry, that's cut off. So you get this springtime depletion in atmospheric mercury in the Arctic, and this is very well dominated. And these are a composite of these monitoring stations in the Arctic. But there's a lot of interest in this region. It's a very sensitive area. There are sensitive populations. And there's this interesting summertime rebound hump that nobody's been able to explain in the atmospheric observations. So with our coupled modeling framework, we've actually been doing a variety of simulations, and this is the work of Jenny Fisher. This paper's in the final stages of review in Nature Geoscience right now. But she's been doing simulations, and she finds that by invoking a large source from Russian rivers of mercury into the surface ocean, which results in enhanced air-sea exchange, you can actually explain. So this is the standard simulation, and this is with the invoked source from rivers. You can actually start to better explain that summer rebound. And okay, so that's significant on its own in that it points to a large source of mercury where we don't have a lot of monitoring data from Russian rivers, and that's important for the ocean on its own. Helps explain the atmospheric observations and sort of demonstrates that utility of using both the oceanic constraints and the atmospheric constraints to try to understand the cycling of mercury in these environments better. This next slide is just to give you a little bit more of an overview of what we've been doing in the surface ocean. And there again, we've been focused a lot on better representation of air-sea exchange in the ocean, because this is such a large term in the global cycle for mercury. So the actual net evasion that you see from the oceans is approximately equivalent to anthropogenic emissions each year. What we've done is try to evoke a simulation that best represents our knowledge of reaction rates. So we have kinetic data for photolytic reduction of inorganic mercury, photooxidation, biotic reduction, and dark oxidation. And those are tied to radiative forcing fields in the model and productivity data from satellites so that we can drive spatial and temporal variability in reaction rates, which will then simulate air-sea exchange seasonally. The other thing that we did, so atmospheric chemists, and I apologize to all the atmospheric chemists in the room, but I get lots of jokes made about me with my colleagues as well. But they like to treat the ocean as a boundary condition. And so many of the early kind of global atmospheric models for mercury, and there are several still, have the ocean as sort of this box which emits but has no kinetic data, and it's not a dynamic interactive term. And so maybe we get the surface ocean, but the subsurface ocean, well, let's just forget about that, right? That can't be possibly relevant. So one of the things we did with this simulation is we started to include a better representation of the subsurface ocean. So the subsurface ocean has been impacted to different levels by anthropogenic emissions in the past, and we can represent, based on simply empirical observations, the differences in concentrations across basins and look at the impact that has on air-sea exchange. So these are all interesting things to do. The subsurface ocean that we work with, again, I said it's fairly coarse resolution. This is actually, Nick and I were having this conversation about SoMAS yesterday, but it's really built around one of his pioneering box models. It's really kind of basin scale resolution, and our focus is really chemistry rather than detailed transport. So we include inputs from rivers and sort of large scale thermohaline circulation, but it's not the sort of detailed transport that you get in the surface ocean and in the atmosphere. But even that provides us with some additional insight onto what the subsurface ocean is doing to the atmosphere. So I'm going to take a step back and just walk you through some of the results now of some of our simulations. So we drive the model with anthropogenic emissions. So this is a view of 2006 anthropogenic emissions. And this is some work done by a PhD student of mine looking at how will mercury emissions change in the future. So this is a 2050 simulation with IPCC growth scenarios. This is the A1B scenario. And what you see again is this sort of continued increase in emissions in Asia and India in particular. With the model, we can then simulate, okay, well, so with those emissions, given what we know of transport and chemistry, what will deposition look like? What does it look like now? And what will it look like in the future? So here's a view of that. And again, you see, this growth in emissions in Asia and India. This is not a huge surprise. We're talking a lot about Asian sources and Indian sources as an area of growth now. So if you look at, we have a tagged tracer capability in the model, so we can track mercury from when it's emitted to when it's deposited and how it cycles through surface reservoirs. And you really see, okay, for anthropogenic emissions, the Asian sources are really dominating present deposition levels. So this is deposition to the ocean, so the fraction of deposition to the ocean from Asian sources. But they're really dominating all term groups. There are some nuances to these data that you can tease out with the model that I think are kind of interesting. where you look at sort of transport efficiencies based on meteorology. So for example, you can see that transport to the Arctic is much more efficient. So per gram of mercury emitted, it'll be more efficiently transported to the Arctic from Europe than other areas, simply based on the location of the polar front and seasonality and things like that. The same thing with North American emissions, probably quite intuitive, have a greater impact on the Atlantic Ocean than other areas. So what does this mean for, when we're trying to think about the exposure pathway, what does this mean for the oceans? So these are data that I compiled a couple of years ago. Again, this is the North Pacific Ocean, and this is a compilation of all the surface observations. And so what you see, so our cruise track was here, these are other cruise tracks in the area. And you see this, so similar, if you think back to what I just showed you, you saw that signal of enhanced deposition from Asian sources. You actually see that show up in the surface seawater measurements. So this is the less than 20 meter surface seawater measurements. This is off the coast of Japan. So that's pretty interesting. This is another simulation with GeoScam showing a tagged deposition from Asian sources. So again, the Asian sources are quite large. The kind of cool science part of this that I thought sort of fell out of these data is that this happens to be at the convergence zone of two major currents where you have, so the Oyashio and the Kuroshio are coming together, and you have sinking and intermediate water formation and then transport across to the eastern Pacific Ocean. So if we look then in eastern Pacific Ocean at our subsurface water profile, so this is the surface ocean and this is depth, this is at different latitudes across our cruise trajectory, then you see in the subsurface ocean an enrichment of mercury just in those subsurface waters at every station relative to the late 80s and 2002 earlier cruises. And so I think this provides some interesting and compelling evidence for enrichment of mercury in the subsurface waters and in the North Pacific Basin observationally from these Asian sources. You have a phenomena to explain this. If we back up a step and say, okay, well, what does that mean then for sort of basin-wide enrichment in mercury levels? And you'll have to excuse me, this is kind of where we're at for availability of data in the mercury field right now, but we only have 3 observational data points. I once put this slide up with a group of water quality modelers and they all laughed at me, so I'm glad none of you did that. But I mean, we're kind of developing hypotheses at this time, but this is just showing a simulation with at present input levels. This is what our subsurface waters are likely to, this is the trajectory they're likely to follow. And so we're saying, well, it looks like the North Pacific is really on the rise because of this increased deposition from Asian sources. The other thing is going back to this idea of mercury as a global pollutant. So we've talked about mercury in the global atmosphere. Obviously, it distributes easily. Mercury transported globally through seafood distribution channels. And you've also now got mercury distribution globally through large-scale ocean circulation, and that's not discussed as much, and I think it's important. So that's looking into the near future. One of the things we have to realize is that there's been a major geographic redistribution of anthropogenic mercury sources over the past few decades. So this is a view of 1990 to 2000 anthropogenic emissions by different regions. So here again, you see this growth in Asian sources. We've had, because of our successful regulatory actions, we've had these large declines in Europe and North America. So what impact has that had on ecosystems? So if we compare trajectories, again, doing the same type of analysis with our model, and again, this is this is looking at the subsurface ocean waters. So we talked a moment ago just about how the North Pacific Ocean appears to be on the rise given current input levels. Similarly, the the Atlantic and the Mediterranean Sea appear to be declining relative to observations. And again, we've talked about this apparent increase from observation, so people tend to believe you better when you don't just present model and simulations, you present real data. And Unfortunately, we don't have a ton, but the anecdotal evidence seemed to support this idea. So there appears to be this increase in concentrations in the North Pacific. And now here are data from the BAT station in Bermuda and the Atlantic. It's hard to read these axes, but the far right begins in 1979, and this is moving toward the present. So you do seem to see, I mean, and some of this can be analytical, so we have to acknowledge that. But you do see this trend of declining concentrations potentially in the Atlantic Ocean. So perhaps we're seeing something there. And it's telling us something about the timescales of response of these ecosystems as well. The other thing that we've looked at is, these are global cruise data for the marine boundary layer. So these are observations collected as ships go through these regions. And consistently they tend to measure high concentrations in the Atlantic Ocean marine boundary layer. So one of the questions that we asked with our model is really, well, what causes that? Why do we see that? In our earlier versions of the model, we couldn't reproduce that until we added the subsurface ocean dynamics. Once we added the subsurface ocean dynamics, where you start to see a difference in the concentrations in the subsurface, so the concentrations in the North Pacific right now are lower than the observed concentrations in the North Atlantic. When you combine that with the various processes driving air sea exchange in the Atlantic, so low productivity combined with high winds and a lot of entrainment of the mixed layer in the winter, and then on an annual basis you see this very large evasion signal from the North Atlantic Ocean. And that starts to help explain those high marine boundary layer concentrations. Again, what our simulation says is it's not just atmospheric deposition then that's important for surface ocean concentrations. It's also subsurface processes. So we really have to understand the role of the ocean and the processes and the dynamics contributing to mercury in the surface layer. So specifically entrainment of mercury in the mixed layer and active pumping are contributing 40% of the mercury in the surface ocean. And that's based on our model. So again, we need this coupled biogeochemical simulation to explain the current global budget. This is a lot of numbers, I realize. One of the points I'd like to make with this slide is mainly, so okay, this is our best understanding of the global biogeochemical cycle at this time. So you've got evasion from the oceans, which is approximately equivalent to anthropogenic emissions and releases from, people talk in roughly a third. So a third coming from anthropogenic sources, a third coming from terrestrial systems, and a third coming from ocean air sea exchange. But I think this is really an incorrect way of viewing this. So regulators will say, okay, well, we can only affect a third of the mercury through, by cutting current anthropogenic releases. But what you have is, sort of a classic biogeochemical phenomena where, you have mercury released from deep reservoirs through anthropogenic emissions, and they're entering these rapidly cycling surface pools. So a lot of that re-evaded mercury is legacy anthropogenic releases. So if you continue to release anthropogenic mercury, then we're basically taking something from a sequestered deep biogeochemical reservoir and moving it into this actively cycling pool where it's going to be around for a long time. If we reduce this amount, we get more than the added benefit of our regulation because we reduce that mercury that would have been introduced to the environment, plus we start to reduce that legacy anthropogenic mercury that's cycling in the environment. And this is a really important kind of idea, I think, for policy. The other thing that you hear is people comparing natural emissions from terrestrial systems and oceans to the magnitude of anthropogenic releases. And they say, oh, well, this idea of a third, a third, a third. But in fact, what we should be comparing the magnitude of anthropogenic emissions to is the geogenic emissions. So what is the natural releases through crustal degassing and volcanoes? And so our anthropogenic emissions are more like a factor of 10 greater than the sort of natural releases that we would see in the environment. So one of our goals of our research group is to understand what is the real enrichment of ecosystems from anthropogenic mercury? And it's very difficult to get at unless you have a full history of mercury from all time. So this has been an exciting collaboration we've had with David Streets from Argonne National Lab. We just put out this paper in ESMT. It just came out in December. And this is actually quite different thinking for the mercury community. So everybody talks about, okay, trends between 1970 to present, huge increases in mercury. And what falls out of this work is really that, okay, well, we've known humans have used mercury since, before, for hundreds and hundreds of years. We do our simulation, just to give you a sense of, from 1450 to present. So I'm only showing 1860 emissions. But there's been mercury cycling in the environment for a long time. These are the different regions. So I focused a lot on Asia now. But if you look back in time, so Asia is in red, the major contributing regions are really North America. And this has to do with gold and silver mining. And it shows up a little better in this particular figure. So early use of mercury for gold and silver mining really released a lot of anthropogenic mercury in the environment. Depending on the time scales required for reassimilation of that anthropogenic mercury into these biogeochemical reservoirs, you still see it out there. And so we have to account for that. We need to think about it if we're understanding impacts of present releases and all-time human impacts. And I find this particularly interesting, maybe just because I like history as well. So this is some work that I did with David on this paper, looking at, okay, well, what are the responses of the different reservoirs, so the relatively rapid surface reservoirs and terrestrial systems. So these are things like ice and labile organic carbon pools lumped together, the atmosphere and the surface ocean, versus the sort of intermediate and armored terrestrial pools, so more recalcitrant carbon pools, the intermediate ocean and the deep ocean. The axes are showing the mercury reservoir from 1450 to present. And the bottom line is that, okay, so again, as I've been talking to you about, the surface reservoirs really track the atmosphere very closely. So just because you've deposited mercury doesn't mean it's going to come right back. So you have this rapid cycling, and then you've got these sort of intermediate timescales for cycling in the ocean, and in the, most of the mercury actually over long timescales is accumulating in the deep ocean. And if you sum sort of the cumulative inputs of mercury to these ecosystems, you end up with quite a bit higher enrichment numbers than we previously saw. So this is something we're looking at. So because we finally have that all-time historical inventory, we can really look at the temporal dynamics of mercury in different reservoirs and understand these questions better. One of the questions driving the field right now, again, focusing just on the 1994 to present period, is this phenomena. This is a paper published in ACP where Franz Slemmer et al. Reported declines in global atmospheric mercury concentrations from a variety of stations, and said the decline is on the order of 20 to 38% in the atmosphere. So if you look at, if you recall now the emissions trajectory was going up. So, I talked to David Streets a lot about this, and he said, well, our slope is perfect, but it's just that the sign is wrong. Okay, it's in the opposite direction. So that's an interesting scientific dilemma. Going back, so what can we learn from the modeling? And this is something my student Helen Amos is working on right now. So we look at the various uncertainties in the global biogeochemical cycle. One of the biggest uncertainties has to do still with the kinetic data for redox dynamics in the surface ocean affecting air-sea exchange, and that's such a huge driver of the global budget. Again, this is just a wild, let's throw it out there hypothesis, but if you had some sort of, so we have no explanation for this decline right now. If you had some sort of consistent change in the rate, so some kind of change in the net reduction in the surface ocean, either through a reduction in the pool of mercury that was being retained through enhanced ocean productivity, if you had a change in the reduction rate, then you can actually explain So it's a big enough handle, and it's the only one that we found right now. So this is the reservoir of mercury in the atmosphere with our global biogeochemical simulation. This is the standard simulation, and this is with a 10, 20, 30, 40, 50% decline in the evasion rate. So again, it's just a sensitivity analysis, but it says that the uncertainty in that term is really important for driving the global budget. It's the only handle that we have right now. We don't know what the sort of the mechanism is, but it's the only one that we can use to explain that. So I've just got a few minutes left, and I want to talk to you about methylmercury. It's one of my favorite subjects. And so we've been talking up to this point about total mercury or inorganic mercury, and the question is, okay, well, how does that relate to methylmercury levels? I think it's a good first proxy. It's not there, but it's, but in some cases we can use it. So I mentioned to you that the Mediterranean is slightly enriched relative to the Atlantic. It seems these are observational data relative to the Pacific. If you look at, say, tuna data, just, first approximation, these are albacore tuna corrected for weight across the different oceans. You see that the slope of the relationship is much higher in the Mediterranean than it is in the Atlantic versus the Pacific. So that, methylation is a first order process, so you roughly expect to see this relationship, but we'd like to do much better than that. So we're really, as a research community, trying to understand where is methylmercury produced. We have relatively little knowledge, again, of these marine environments. This is just to kind of bring you back to what we're talking about. So the majority of mercury deposited from the atmosphere is going to be in this divalent form. There's a microbially mediated reaction. The communities that have been identified so far are sulfate and iron reducers. I suspect there are many more that we just don't understand at this point and haven't identified yet, but they mediate conversion depending on the bioavailability of that inorganic mercury to methylmercury. Methylmercury is the only species that bioaccumulates in fish, so all of those trophic dynamics are very important as well. So the dominant hypothesis for the last several years has really been that ocean margins are the source of methylmercury for pelagic marine fish. I don't personally believe that. I have to warn you, most of the community still believes that. I really don't believe that, though. So, and I'll tell you why. So if we think so obviously methylmercury production in sediments it's very important for benthic communities or any kind of food web that has a link to the benthic food chain. But for purely pelagic food webs, then we can just let's take a step back and think about it simply. So people often talk about sediment to water diffusion of methylmercury. So you have methylmercury produced at the redox interface in sediments, and then you have that diffusing into the water column where it provides a source for marine fish. If you think about it from a modeling perspective, if you've got any methylmercury in the water, some of it's going to absorb to solids and settle, and you also have that influx term from resuspension. So you want to do a full mass balance for where that mercury is coming from. But our sort of knowledge in this area has come from some very broad scaling of Long Island Sound numbers, you guys will like that, to the entire globe. So there's a sediment to water, I'm not kidding here at all. So there's a sediment water diffusion rate that Chad Hammerschmidt et al. Measured of 40 picomoles per meter squared per day. And they scaled that to the ocean margin areas globally to get about 0.52 megamoles per year. The problem with that is that it doesn't, if you're going to come up with a number, at least come up, do your two-way flux calculation. So in another area, and I acknowledge that this is hydrodynamically a very different environment, but this is a paper I published in 2010. If you look at, so we measured very high methylation rates in these sediments, and you do see a substantial sediment to water diffusion rate, but the settling term, because of the concentrations measured in the water column and on particulates, actually makes the sediments a net sink for methylmercury. So it doesn't quite get us there yet. I'm not saying this is true for all coastal environments. I just think, and I'm going to quickly run through the sort of marine water column work that we've done now, It's very difficult to come up with the same order of magnitude of numbers if you have methylation occurring in open ocean waters, which we have substantial evidence for now. This is the cruise track from the North Pacific that I mentioned to you before. This was a cruise in 2006 on the P16N cruise track. And these are some new data we have that I'm writing up right now from the Atlantic Ocean. On both of these cruises, we've measured total mercury and methylated species, so both methylmercury and dimethylmercury. And one of the things that we found in the North Pacific was really this, and this, you know, people had stopped talking about methylmercury in open ocean waters. These are very high levels of methylmercury. You know, we're talking about 20% of the total mercury burden in the subsurface waters. So you see detectable methylmercury in the surface waters, but really at peak in these subsurface waters, which is very closely in the North Pacific associated with the oxycline position. So basically what we're seeing, and you see it across a number of different cruise tracks now, is you have algae in the surface ocean, you have absorption of inorganic mercury to those algae, delivery, and then accumulation in the subsurface waters. Where you have a productive region, you seem to have more methylated species. So there's in those subsurface waters that are getting a lot of organic matter decomposition. You have a lot of sort of heterotrophic bacteria, and you're seeing a lot of methylated mercury species. So it's pretty cool. From those data, I developed this relationship, which is a proxy between methylated mercury concentrations in ocean seawater and the organic carbon remineralization rate. So again, methylmercury production is linked to basically the ocean biological pump and the remineralization rate of organic carbon, likely a proxy for heterotrophic bacterial activity. I thought this was interesting. It's great from a modeling perspective because it means that we've decoupled our ability to kind of look at distributions of methylmercury from the very minimal observations that we have. So we can use this relationship for organic carbon remineralization rate. We can use the nutrient data and the oxygen data and water mass age to start to predict methylmercury. I know I'm running out of time here. I just wanted to say that this kind of relationship has been reproduced across a number of different ocean basins. So the same type of phenomena. So here you're looking at the nutrients, oxygen, AOU. These are all things that feed into that calculation of organic carbon remineralization rate. This is the Indian Ocean data now compared to the North Pacific data. So the Indian Ocean cruise track that we sampled is a very oligotrophic area. There's not a lot of productivity. It's not that interesting, to be honest, except it provides an interesting test for this hypothesis. So as expected, the methylmercury levels are quite a bit lower. And if we go on and plot methylated mercury species relative to organic carbon remineralization rates, it looks like I made it up, I think. You know, this is exciting, I think, from the perspective of now being able to say something about hypothetical variability spatially and temporally in methylmercury production. Methylmercury production in ocean waters, so one more point, the fish levels roughly seem to correlate with this idea. So this is again from the North Pacific Ocean. The concentrations, this is a paper by Choi et al. In PNAS. The deeper the migratory patterns of the fish and the deeper the prey items, the higher their mercury burden. So the picture is starting to come together. Just to bring it full circle, this is important for the temporal response of the oceans, because if you have methylmercury production in just the subsurface waters, so say 200 to 500 meters of the ocean, that's going to respond much faster than, say, a watershed-dominated system. This is a simulation for a coastal plain river, but it takes a long time for mercury to work its way through watersheds. And those are major inputs to many coastal regions. So from a policy perspective, the response times of these upper ocean waters of major basins will be much faster than if the major source of methylmercury production is in these ocean margin areas. So just to wrap it up, I guess what I've tried to say very rapidly with lots of information here. Ocean fish are really the main vector of human exposure for most individuals in the U.S. population. So there's a whole nother set of questions about high-risk groups, but for most people, we really need to look and understand mercury dynamics in ocean systems a bit better. Declines in atmospheric declines in atmospheric emissions from human sources will likely be realized in fish faster than previously anticipated, given our new knowledge of locations of methylmercury formation. I think this link to organic carbon remineralization and heterotrophic bacterial activity really needs to be explored on a mechanistic basis now to try to understand what are those communities, how do they enter the base of the food web. Lots of really fun science to be done there. And the next phase in our modeling work is actually now linking these simulations of ocean water concentrations to uptake at the base of the food web. And we're actively working on models. It's difficult to do the same scale of modeling for bioaccumulation, but we're working on bioaccumulation in different representative food webs across different basins. And so just as a last slide, I'd like to acknowledge our large team Mercury at Harvard, many great graduate students, and I co-lead this group with Daniel Jacob in the School of Engineering and Applied Sciences. We've also had, obviously, many excellent collaborators on this work, and I'd like to acknowledge our funding sources. Thanks very much, guys.
I'm sure Elsie would be happy to address any questions. Fire away.
Yeah.
Your projection with the 3 data points was interesting, you know, and expected a laugh or whatever. But what I noticed from those 3 data points and from the, I suppose they correspond to the profiles you showed in the slides earlier. You know, one can overfit 3 data points by eye. It's hard to avoid. But it looks like from 1987 to 2002, no change. And then 2006 is drastically different. And your interpretation is that this is representing an upward trend. But is there any reason to think that either you get a large amount of fluctuation year to year, or that there would be catastrophic, you know, sort of punctuated changes in the profiles?
Yeah. I guess the first thing I should point out is those were 2 totally different, so the simulation itself is not tied to those data at all.
Sure.
So they're independent data points. So I wasn't trying to fit the data points at all. I was just letting you look at the data points in comparison to what our models
No,
are.
I'm doing the fitting by myself. Just wondering about what 3 points mean. You know?
Yeah, I mean, it's really hard to infer a trend from 3 points, I think.
Sure.
I think because we have such limited data from these systems, we have to kind of, it's almost like, you know, piecing together what story, what lines of the story fit together to provide some weight of evidence. So I don't think there's any reason to think that you get a rapid change in concentrations between 2002 and 2006, given our knowledge of emissions.
It was almost the same thing with the Caribbean data. It seemed as though all years were on one side except for 1970 and the other. There was just no, it's the missing link. What happens in between?
Yeah, I mean, it's difficult when you don't have the data to fill everything in. There is some seasonal variability depending on overturning of the water, and if you're sampling from a stratified area and with a mixed layer depth theory. So you do see some numbers, and that they're not, those cruises aren't all in the same season. So that does kind of move them closer together, further apart, depending on that. But it's not enough to explain, say, the systematic difference we saw across all the stations on the North Pacific. But I mean, I think we have to be very hesitant in inferring it. I mean, I can hypothesize that we have a temporal trend. I don't think we can conclusively say that we see something. Right now, we're looking for, as I said, lines of evidence. Did you have something to add?
No, I had a different question.
Okay.
What, the third and a third and a third,
Mm-hmm.
I think I heard you say that the mercury that's coming from the ocean, coming from the land, includes mercury that originally was put into the atmosphere by anthropogenic.
Mm-hmm.
Is that correct?
Yes.
Okay.
Yeah. That's why it's not So the point I was trying to make with that is that the third that you hear about, and people say, oh, well, then okay, that means 2/3 are natural, right? They're coming from the oceans and the land. And I don't think that's the appropriate takeaway message. So, go ahead.
So you made a, I thought, very convincing case that if you want to understand exposure of mercury to open ocean fish, you have to use this dynamic that you've been talking about. But there are a lot of fish that, anadromous, diadromous fish particularly, that are tied to the coastal zone. And my impression, well, I know that fish mercury levels in, let's say, our region here have been declining. And it seems to be a response to management. But it also implies from that their exposure to mercury maybe very much is tied to some of these local benthic processes and things, and maybe they don't affect open ocean things. So maybe there really are very different management strategies that one thinks about when one thinks about anadromous fish and the open ocean fish.
Yeah, I absolutely agree with you. And also, so just adding a layer on that, there's you have to be a little bit careful when you frame it. So I was trying to present a global picture and why this is relevant. But when you start to think about susceptible populations, and susceptible populations that include people who consume from local water bodies, then you really start to see the impacts of regional and domestic management actions. So you impact those fisheries and you impact the people who are harvesting resources from those fisheries themselves. And the processes vary across ecosystems as well. So, how do I pick? Go ahead.
Your discussion of what's happening in the deeper ocean leads me to wonder the relative importance of organisms that specialize in the oxygen. So is how important is their uptake and then trophic transfer versus the methylation there and transport areas outside of the oxygen.
Yeah, then that's an excellent question. So that's something that
That's
Nick
my
has been thinking about. So then, like, what is the vector of entry into the food chain? So you have like vertically migrating zooplankton picking up the methylmercury in subsurface waters? Do you have, is it diffusion limited for sort of upward transport? These are, big questions that we need to answer as a field. Go ahead.
I was wondering about the sushi and the adult, like the toxicity levels of the. There must be some sort of correlation between the incredible uptick in like sushi, restaurants and sushi popularity and this phenomenon. I mean, it was just like the famous example. But are you aware of any like statistics correlations on a population scale that this is true?
Well, not so much linked directly to the sushi, but there's an interesting, so for most contaminants, the lower socioeconomic groups tend to be the most highly exposed, and for mercury it tends to be the reverse. So the highest socioeconomic groups tend to have the highest blood mercury levels because of the preferences for things like sushi. So you get on one end, the subsistence fishers are very high, then the lower socioeconomic groups being somewhat low, and then this rise, and then in the highest socioeconomic groups that are consuming a lot of these expensive pelagic, large fish, sushi delicacies, they're very high in blood mercury levels. So, and I mean, a cynic would argue that's part of the reason why mercury has received so much attention as a contaminant. Just throwing it out there. There was one over here first. Go ahead.
This is going back to the beginning of the talk when you were looking at the pattern of deposition with the model. There was one with bromine, and then there was one with the OH and ozone. But when you did that, there was not much change over India and India. In the pattern.
There's a lot of change in the spatial pattern. There's not a lot of change in the magnitude of deposition. So it just has to do with where the distribution of the oxidants are in the atmosphere. I think it's up further. Right there. So, I mean, the main change is that, the sources of bromine in the atmosphere are more distributed to the regions where you see these deposition, whereas the dominance of and the transport patterns for ozone and OH. And the reactions are occurring in the mid-latitudes and subtropical areas. So, is that what you're asking, or?
Yeah, I was just wondering why,
Yeah.
if you look at the east, in the Asian region, over India and
Over
China,
India and China. Yeah, it just,
it still remain. They didn't quite change compared.
yeah, yeah. Yeah, no, it's just based on the distribution of the oxidants in the atmosphere. So you see a lot of changes, not so much in the mid-latitudes, but in the polar regions. And that's just the way that the data fall out.
Which model does the observations confirm?
Well, that's a tricky question. So you could read Holmes et al. It's quite I think it's 26 pages. It's an ACP. It's a great paper. We believe very strongly it's bromine based on the diurnal kinetic data. So if you look at the observational data for changes in reactive gaseous mercury concentrations in the atmosphere, then I think the case more strongly supports bromine. There are people who still believe fairly strongly that ozone and OH are reasonable. They tend to already have tools in place and don't want to adapt their models, is my impression. But I mean, the reality is, again, you can make a case for both. I think the case is slightly more strongly in the favor of bromine. There may be another oxidant. So bromine isn't perfect. And there's a lot of uncertainty in bromine data. So that's part of the problem, right? So bromine is its own field. Specifying accurately the global mean concentrations of bromine adds an additional layer of uncertainty here. But the kinetic data, and again, you should refer to Holmes et al. To get a really comprehensive discussion of that, but it really does seem to support bromine, I think, as the major oxidant. And some of the lifetime estimates for mercury in the atmosphere. So there's, and again, I'm not a very good atmospheric chemist, actually. I think I said that already, but Daniel Jacob is actively pursuing this as an area of research, so he can probably provide a more concrete answer soon.
Can that happen within seawater as well, bromine oxidation, or is that not?
It's a good question. It's not the same. I mean, we don't have the mechanistic data on speciation for what is actually catalyzing. Our measurements are quite limited, so we measure more in sort of under these light conditions with filtered water versus unfiltered water, in the dark, in the light. So it's difficult to answer sometimes, but thermodynamically, yes.
There's been a very rapid increase in the use of compact fluorescent lights worldwide. In some countries, in fact, are in the process of outlawing incandescent lights. And these bulbs contain trace amounts of mercury. Now, is that likely to be a tiny source compared to, say, burning fossil fuels, or what?
So it can be a substantial source. The argument that the fluorescent bulb manufacturers make is that the energy that you save with the fluorescent bulb is actually results in a net, lower quantity of mercury released to the environment than if you burned all that energy from a coal-fired power plant.
So that means it's measurable, and it could be. They claim it's a term in the global budget. So we have a graduate student actually right now. So one of the uncertainties. So I showed you that declining trend in the atmosphere. One of our potential uncertainties is what about products? There's been a ton of mercury used in products globally, not just fluorescent bulbs, but over time. And what's the fate of the mercury in those products? So some of it's combusted and it goes back to the atmosphere, and we account for that. But what if it goes into a landfill? What if it's broken? So how can we get a better handle on those numbers And then if you remember, like if you release that number to a, one of these active recycling surface reservoirs, it's going right back up to the atmosphere, right? And then it's going to bounce around for a long time. So products do have a measurable impact. They're not explicit. I haven't explicitly accounted for that in this work.
On Long Island, we burn a lot of our trash. Now, you're supposed to recycle these things, but I imagine...
I think it's about 2 milligrams per bulb. Does that sound right to you? Yeah, that's the number that I remember. Does that answer your question? It's substantial, but coal-fired power versus energy savings from fluorescent bulbs. So. It's more of a concern in broken bulbs. That's been more of the discussion. So breakage of those bulbs and then people inhaling the mercury. So there was a case in Massachusetts that got a lot of media attention where, the manufacturing groups didn't want to put a warning for disposal of those bulbs. And they're having this discussion with EPA, and it's a no, we don't want to scare people. And about the same time, of course, they didn't want to do anything. About the same time, some woman broke a bulb, and she had a toddler running around. And so she brought in like a hazmat group to measure the concentration above her carpet, and then it blew up, and it was, Washington Post, all these things, big scandal in DC. And now there's labeling and a lot of discussion. So it would be better for them to label correct disposal, but I think the health concern is more acute toxicity from inhalation of elemental mercury if you break it on your floor and then lean over and breathe it all in at once. And then it's, and then there's the longer term issue.
Any other questions? Thank you very much, Elsie.